Welcome to part 2 of 3 of this demo video series on Live Volume with Auto Failover for Microsoft. Now that we have reviewed Live Volume core features and functionality, let's talk in more detail now about the latest enhancement to Live Volume, which is the addition of Live Volume Automatic Failover. This enhancement allows administrators to configure a primary Live Volume to automatically fail over to another storage center if an unplanned disaster takes the primary Live Volume offline. It is important to point out that as we talk about this latest Live Volume feature enhancement, that all of the previous Live Volume functionality is still fully supported and available to administrators. As was stated previously, Auto Failover was introduced with SCOS 6.7, but was compatible at that time with VMware environments only. To learn more about Live Volume with Auto Failover for VMware, please visit Dell Tech Center and review the Live Volume Solutions Guide mentioned previously, along with a demo video showing how this works with VMware. With SCOS 7.1, Live Volume with Automatic Failover support was expanded to include Microsoft in addition to VMware. In this part of the video, we'll first review the Dell SC Series storage requirements, followed by Microsoft requirements. After that, we'll take a deeper dive into how Live Volume with Auto Failover works with Microsoft, followed by covering Live Volume with Auto Failover behavior given a number of different DR failure scenarios. The Dell SC Series storage requirements are as follows. A pair of SC Series controllers that are sized correctly to support the workload that will be using Live Volume. Using similar or dissimilar SC Series storage is supported, but because Live Volume with Auto Failover requires synchronous replication, keep in mind that the overall performance will be no greater than that of the lower performing array if dissimilar storage hardware is used. SCOS 7.1 or newer. The storage centers must support Live Volume and have the feature license for Live Volume applied. The storage centers must be well connected to each other with at least 1 gigabit per second or greater bandwidth available for replication and proxy data between them, with no more than about 5 to 10 milliseconds of latency for any data paths to avoid performance degradation of critical workloads. While higher latencies might be tolerable for some workloads, anything over 10 milliseconds may start to cause noticeable performance degradation. The Dell Storage Manager version 2016 R2, specifically the data collector component installed at a third location, which could include a cloud-based service. While Dell Storage Manager has been around for many years, it has taken on a new role with Live Volume with Auto Failover, as the DSM data collector can now act as a quorum witness and tiebreaker when determining if a primary Live Volume should automatically fail over. Placement of the tiebreaker DSM data collector at a third site is critical to the design so as to avoid site bias, as will be discussed later when we talk about failure scenarios. Administrators can and still should use local instances of DSM at either the primary or secondary sites for day-to-day storage administration, monitoring, alerting, and so forth. The DSM instance at the third site should ideally be dedicated to performing quorum witness and tiebreaker roles. Connectivity from the DSM acting as the quorum witness and tiebreaker must not exceed 200 milliseconds of round-trip latency to each storage center. Unreliable connections will also interfere with the ability of the DSM to perform its role properly. Live Volume with Auto Failover requires that a Live Volume be configured to use synchronous replication in high availability mode. This is configured by editing the properties of the Live Volume. Once synchronous HA is enabled for a Live Volume, then at the bottom of the configuration screen, the Failover Automatically and Restore Automatically options become visible. Enabling the Failover Automatically option will, by default, enable the Restore Automatically option as well. Now let's go over the Microsoft requirements. Physical host cluster nodes require Server 2012 or newer. Physical Hyper-V cluster nodes also require Server 2012 or newer. Regardless of the type of physical cluster, both non-uniform and uniform server mappings with MPIO are supported. There are also 3 types of supported guest VM clusters. The first is guest VM clusters that use shared virtual hard disks for cluster disks. This requires Server 2012 R2 Hyper-V hosts and Server 2012 or newer guest VMs. The second is guest VM clusters that use in-guest iSCSI for cluster disks. The host servers must be running Server 2012 or newer. VMware 5.5 or 6.0 hosts are also supported. Guest VMs must be running Server 2012 or newer. Similar to physical clusters, guest VM clusters using in-guest iSCSI volumes also support non-uniform and uniform volume mappings. The third type is guest VM clusters on VMware 5.5 or 6.0 hosts that utilize physical raw device mappings for their cluster disks. The guest VM OS must be Server 2012 or newer. Both non-uniform and uniform server mappings are supported with VMware hosts as well. Let's review briefly the options for configuring a quorum witness with Microsoft clustering. With Live Volume Auto Failover, when clustering Windows hosts, Hyper-V hosts, or guest VMs, providing a file share witness or a disk witness is supported and is especially important if both sites A and B have the same number of nodes. Given a site failure at A or B, the quorum witness can serve as a tiebreaker, allowing the cluster resources on the nodes at the surviving site to stay online. With Live Volume Auto Failover, the best design is a file share witness that is configured at a third site. Given a site failure, the surviving site will have continuous, uninterrupted access to the file share witness. This is the most fault-tolerant design for both physical clusters and guest VM clusters. If providing a file share witness at a third site is not possible, then a disk witness can also be configured, but this design is less fault-tolerant and may require a manual recovery of the quorum witness at the surviving site given a complete site failure that affects the current owner of the quorum disk. For more information on best practices for configuring a Microsoft Quorum Witness for your Live Volume Auto Failover environment, please consult the Synchronous Replication and Live Volume Solution Guide mentioned previously. As of the release of SCOS 7.1, the Live Volume Auto Failover feature has not been tested with the following configurations and are therefore not supported. Cluster configurations, where the host or guest operating system is prior to Server 2012, guest VM clusters that utilize either virtual fiber channel disks or pass-through disks as cluster disks. Now let's examine how Live Volume with Auto Failover works. Given the power and flexibility of Live Volume, administrators have a lot of latitude to design an environment that best suits their DR needs. The primary and secondary sites could represent two different racks within the same data center, different data centers within the same building, different buildings within the same campus, or locations that are separated geographically but yet are close enough to ensure acceptable bandwidth and latency performance for the protected workload. For purposes of this video, we'll use a simple configuration consisting of a physical 2-node Hyper-V cluster with a node at each location in a stretch cluster configuration. The physical servers are well connected and configured to use uniform server mappings with MPIO round robin. On the 2-node cluster, we have a guest VM cluster that is configured to use shared virtual hard disks for its quorum and cluster disks. We will also assume that Live Volume with Auto Failover is enabled for the abstracted volume, which is actually, in this case, a cluster shared volume for the 2-node physical cluster. This contains the shared VHDs for the guest VMs, and we will also assume that all other prerequisites have been met from a bandwidth, latency, and a design standpoint, including the presence of the DSM tiebreaker at a third site. Before going further, while these elements are still present and functioning, we'll remove the shared VHD layer just to simplify the diagram a little bit. With our example configuration in place, let's walk through step by step what happens when there is an unplanned DR event that takes the primary storage center and the primary Live Volume offline. First, we'll introduce I/O from our host servers that is being generated by the VM workload, showing how data reads and writes interact with the primary Live Volume directly over primary paths shown in green. I/O using secondary paths in red is proxied to the primary Live Volume through Storage Center B. Next, we'll introduce a storage center failure that results in the primary Live Volume going offline. From the perspective of the host servers, they continue to see the same abstracted volume, however with fewer data paths now available. I/O is paused briefly because the primary live volume is no longer available to process reads and writes, and concurrent with this, the DSM at the third site also loses connectivity to the storage center at the primary site. At this point, the clock starts ticking. Because we have a limited amount of time to complete automatic failover so that we don't exceed timeout settings on the host servers, the DSM will promote the secondary live volume to primary status in about 30 seconds or less. The secondary data paths will now serve as the primary data paths for the host and guest I/O, and the I/O from the workload will resume once the new primary live volume is able to accept read and write I/O. The recovery point objective for this event is effectively 0 because we are using synchronous replication, which ensures no data loss between the two storage systems, and the recovery time objective is typically going to be somewhere between 30 to 60 seconds for an effective RTO of 0, assuming that the host and workload can tolerate a short period where the I/O is paused. Although live volume auto failover will complete in about 30 seconds or less, it may take host servers a bit longer to retry the available data paths and resume I/O, and this might take, in the case of Windows hosts, up to an additional 30 seconds. It is therefore extremely important to ensure that your Windows servers are configured with appropriate timeout settings so that when I/O is paused briefly, the host servers keep SAN volumes online. Now, let's take a look at how live volume can automatically recover the live volume pair once the primary storage system comes back online. This feature is enabled by default on a volume, as shown here, anytime failover automatically is enabled. Let's bring the primary system back online. The DSM reestablishes connectivity to the primary storage center, but DSM prevents the original live volume from coming back online as primary so as to avoid an undesirable split brain scenario where data might otherwise be written to both volumes, causing data inconsistencies or corruption. To prevent split brain, the DSM brings the live volume online, but as the secondary live volume. Replication between the storage centers is again reestablished, as are the host server data paths, which the host servers can begin using again for servicing I/O in a round-robin fashion. Once the replication has caught up and achieves a 100% status, the live volume achieves what is called protected state, meaning that if a failure now occurs at the secondary site, automatic failover would occur back to the primary site. And while the replication catches up, the workload continues to use the primary live volume. In this example, we will use the DSM client to initiate a manual role swap to move the primary live volume back to the primary site again. And I/O resumes over the original data paths that were in place before the DR event occurred. Now that we have shown what happens given a DR scenario involving a storage center failure, let's review a few other failure scenarios that would also cause automatic failover, starting with a more disruptive event, a complete site failure. As before, we'll begin by introducing I/O from the VM workload. As can be seen here, the site failure affects not only the storage, but also the host located at Site A. In addition to losing data paths, this outage also affects guest VM cluster and also the host cluster. As before, the DSM promotes the secondary live volume to primary status, and I/O resumes from the surviving Hyper-V server and guest. The ability of Hyper-V and the guest VM cluster to survive losing nodes is a function of Microsoft design, and in most cases, a site outage may require administrator intervention to bring the workload online at the secondary site. Not because of a storage outage, but because of resiliency limitations with Microsoft clustering. The point we want to make here is that access to the live volume data by hosts and guests at the secondary site is preserved despite the disaster at Site A. In addition to a storage center or site failure, another scenario that would cause a live volume failover would be a back-end storage failure. As before, we'll introduce I/O and then show what happens if there is a distro failure. The result is very similar to a complete storage controller failure in the way that DSM reacts to the event and promotes the secondary live volume to primary status in about 30 seconds or less. It is also important to understand that there are many events that, while they may impact the environment in some way, do not constitute a disaster from the perspective of live volume and will therefore not result in a primary live volume automatically failing over. Administrators will always retain the ability to perform a manual role swap in cases where a planned outage will impact a workload, even if a live volume is configured for automatic failover. Let's review some of the more common scenarios that will not result in a live volume automatic failover. These include a single controller outage, reboot, or failure within a storage center that has dual controllers, as long as at least one controller is online and functioning. This includes graceful, managed, orderly controller reboots one at a time, as when performing a controller OS upgrade. A single drive failure or other limited disk failure that is remedied by hot spare coverage. A failure of DSM or a third site failure that brings down the DSM. Loss of connectivity between the DSM and one or both storage centers. Any type of failure with the storage center hosting the secondary live volume, including a controller, a storage center, or site failure. A replication failure between the primary storage center and the secondary storage center. And finally, why it may affect the workload, any type of failure with the hosts, the guests, hosts or guest clusters, or data paths between the hosts, the guests, and storage centers will not in and of themselves cause a primary live volume to fail over. The final scenario we will show is what happens if there is a loss of quorum. While this is an unlikely scenario, it highlights the importance of ensuring that the DSM is placed at a third site with reliable data connections to prevent site bias. Loss of quorum occurs when the primary site becomes completely isolated and can't see either the DSM or the secondary site. This might happen given a failure of the DSM or the third site, concurrent with a failure at the secondary site that takes the secondary live volume offline. Loss of quorum could also be caused by concurrent connectivity failures that completely isolate the primary site, even though the DSM and the secondary site might still be online. This is why it is very important that the connections between the sites be reliable, and is why the DSM should not be co-located at the secondary site, because a site outage there would inadvertently cause loss of quorum and the primary live volume would go offline. If we assume that the live volume replication is 100% in sync, which is going to be typical in most cases, at the time of the quorum loss, the primary live volume will go offline. This is because the primary live volume must assume that by becoming completely isolated, that the DSM and secondary site are still online, and that the secondary live volume might now be taking over as primary. If for some reason the live volume is not 100% in sync at the time the primary site becomes completely isolated, which would not be a typical situation, then the primary live volume will not go offline given a loss of quorum. The storage center with the primary live volume would know, given this situation, that the secondary live volume is unable to assume a primary role because it was out of sync when quorum was lost. That concludes part 2 of 3 of this demo video series. Please continue by viewing part 3.